Hi again. I just was uploading the previous video of XPS and I saw someone commented on my video. Thank you so much. I primarily make these videos to just share with my friends. I didn't know people out there were seeing this. Thank you. It was very nice of you. So now we'll start with the second part of XPS, that is analyzing the survey spectrum. Now here we have the survey spectrum. So it is the same one that we have previously used. Let's say this one actually the material. First let's remove all these notions. So this is the blank survey spectrum that I have, and this material has this high entropy oxide and it has a lot of elements. So I'll tell you how to analyze each one, or let's say I'll analyze only three of these COM and Ni. Whatever your sample is, you can analyze. I don't want to do the full 5 or 6 element analysis in this one, but I'll tell you the process to do. So last video we saw how to mark these things, CO2p, Mn2p, all these things. Then to do the analysis, we have something called as relative scattering factors. That is when your XPS works, each element scatters some part, or let's say uh, each element has some scattering power of the photoelectron. So lighter elements they scatter less, like let's say lithium. If you go to the element library, there is not only periodic table but also element table here, which you can see RSF, which is here. See RSF sensitivity factor, not scattering, it is relative sensitivity factor. Each element has a sensitivity factor of its own. So all the CO2p or Mn2p, CO2s or CO2s, everything has thing. And the thing is that some elements are very sensitive to the photoelectron, and so and some are not, and some have relatively less area of peak because they are smaller in atomic number, and some high atomic number elements they have bigger area of this peak area. So when we can calculate the stoichiometry using this peak area and the sensitivity factors. To do that, first I suggest you to read this one. There is a very good website, xpsfitting.com, and here you can see all of this, how to do the fitting and everything. You can see here. Then you also have the CasaXPS tips and how to do better fitting, uh, and they are very good videos than what I am making. And then I'll just see where the RSF factors are, relative sensitivity factors. So you can see like how these are used, and you can read all about them. But this is the primary table that we'll be using, or the one present in Casa. Use either one of these, like either this or that. I'd suggest better use this because this is more based on a source there from, like, this is based on a literature source. So also you can calculate like RSF of any element of 3 by 2 is RSF into of that element into 2 by 3. So if you want to calculate, let's say S2P, or like S does not have, but let's say Ti2P. So you have Ti2P is 2.001, Ti2P 3 by 2 is 2.001 into 2 by 3. So you get the RS of Ti2P 3 by 2. So this is what the formulas are also. Then after that, let's say I have these three elements. First, I identify each, same as previous. So my cobalt is this, manganese is this, and then nickel is this. So I have these three peaks. I'm removing them, or I'll just put one element. Then I make a box here. So, and then this is the zoom in icon, but you have to make a box for it to zoom in. So you have CO2p 1 by 2 and 3 by 2. You can observe it is the same pattern that we had obtained in here. See, because this is a high resolution data, so you get better. Once you've done that, define regions. Here we don't use components, we use regions. So define the region. I think I've done. I have to zoom in a bit better. Yeah, now it is fine. So now that the region is defined, you don't need to be truly accurate in this, but as accurate as possible, because most of the shapes have very less data points. If you plot it as a uh, like using dot instead of the line, you can see there will be less data points as compared to the high resolution spectrum. Once you have done this, put here CO2P. Okay, now enter. Always remember to press enter. Then go to this table. Sorry. Then go to this table and then see the value of CO2P. Here you have CO2P 3.590. Let's say you are only fitting one of these, then you use the CO2P 3 by 2 or something, but we are fitting both in same region 3.590. So write it here 3.590, enter, then zoom out, then let's see where NI is here. We again zoom in, create a region, then NI2P, again check in the database, NI2P is 4.044, then zoom out, do the same for manganese also, Mn2P, you have Mn2P 3 by 2 is 1.773. So using this formula, you can calculate it as 1.773 equal to RSFP into 3 2 by 3, so it is into 3 by 2. So 1.773 into 3 upon 2, 2.6595. So 2.6595. You've got this. This has many elements. I'm just doing 3 of them as an example. You have to account for all these peaks and all the elements. If your material does not, this is a C1, I think, yeah, this is the C1s peak. So whatever peaks you have, if you don't have C1s, just leave this peak and account rest of them. You don't need to go for LMM and these things. You just need to do 2P, 2S, 3D, 3P, whatever is there. Then once you do that, again go to processing. Sorry, not processing, this pencil icon, title and ocean. Then here go to component, mm, ratio, no, quantification, sorry, quantification, table type regions, just components and apply. Okay, does not come. Mm, include RSF, include weight percent, use tag field, apply. I don't know where it's coming. Data, let us see. Okay, generally there is a, in here you can see all the a table kind of thing where you have these things. So you get here a table which says RSF equal to this much, and I'll show you an example for that if I can. So this is the table that comes up. So you have your position, area, atomic percent, all these things. Basically this is what comes up, but you don't need it. in just in case for your labeling and all. But anyways, we do this calculation separately. So better what we take is this area. You have your area 143 whatever. So you need to make a table in Excel. It is better to make in Excel. I'm just showing in PPT how it is to be done. 1437225.9 1696124.4 1208.486.8. So this is CONINMN CO2P and MN. Then you have your RSF 3.59, 4.044 and 2.6595. So once you have these two values, take all the values from that spectra, and then here you normalize this area with respect to the RSF. So this is just area upon RSF. So I'll show for one, and you can automate this using an Excel, that is better. So 143.722.7225.9 upon 3.59 is 4. Okay, so I think I need to do, because here there is also this one parameter. Okay, I'll just copy these things. Yeah, so x equal to a upon RSF, so we'll just put a upon RSF. Then we do the same for all, and then we have to sum these things because that's a sigma term. This is this xi, and sigma xi is just this one. So we just put equal to sum of. So I'm not just leaving the columns blank, but you can create a table out of Excel. So here you have equal to this upon this equal to this upon this. Just don't use this one because the Excel does not take it. You have to do it individually. But once you create this table, you can use for multiple works. Then you have atomic percentage. This is just multiply by 100. So this 31.42. So just this one into 100. So this is the total percentage as of now. This is wrong, I know, because there are more elements to analyze. And then, but if you these were all the only three elements, then this is the atomic percentage what we got from XPS. And using this, you can try this stoichiometry also. Just convert this atomic percentage into atomic fraction, and you have this stoichiometry. So this is how we do this stoichiometry from survey spectra. And that's it. Have a good day.